When the United States entered World War II, American military planners believed they already had a fighter aircraft that could handle anything the enemy put in the sky. That aircraft was the Lockheed P-38 Lightning. With its twin engines, twin tail booms, and heavy nose-mounted firepower, the P-38 looked more like a science fiction machine than a traditional fighter. It was fast, powerful, and packed with technology no other nation had successfully fielded at the time. On paper, the Lightning was superior. It could fly higher than most enemy fighters, dive faster, and deliver devastating fire without the need for gun synchronization. Engineers were confident. Commanders were optimistic. Pilots, at least at first, felt proud to fly it. Then, American pilots met the Japanese Zero. Over the Pacific Ocean, confidence disappeared quickly. The Mitsubishi A6M Zero was smaller, lighter, and shockingly agile. In close-range dogfights, it seemed to turn effortlessly while heavier American fighters struggled to keep up. P-38 pilots reported that once a Zero got behind them, survival depended more on luck than skill. Mission reports told a disturbing story. The Lightning was fast in straight flight, but in tight maneuvers, its controls felt heavy and uncooperative. Pilots pulled harder, but the aircraft responded slowly. Some described the sensation as fighting the airplane instead of flying it. Losses began to mount. Back in the United States, engineers were confused. The P-38 had passed every test. Wind tunnel data showed nothing wrong. Structurally, mechanically, the aircraft was sound. Yet combat told a different story. Something was wrong, not broken, not damaged, but wrong. And the people who would eventually uncover the problem were not senior engineers, famous designers, or decorated aces. They were mechanics working under the Pacific sun, listening carefully to pilots no one else was truly hearing. To understand why American pilots were struggling in the skies over the Pacific, it's necessary to understand the enemy they were facing. The Japanese Mitsubishi A6M Zero was not built like American fighters. It followed a completely different philosophy, one that prioritized agility above everything else. The Zero was extremely light. Japanese engineers achieved this by removing anything they believed was unnecessary for combat. There was no pilot armor. Fuel tanks were not self-sealing. Structural strength was sacrificed wherever possible to reduce weight. The result was an aircraft that could turn tighter, climb faster at low speeds, and respond instantly to control inputs. In a classic dogfight, the Zero was deadly. Japanese pilots knew exactly how to use this advantage. They avoided high-speed dives and instead pulled enemy fighters into turning battles, where the Zero dominated. Once an American pilot committed to a turn, escape became difficult. The Zero would tighten its circle, slip behind the enemy aircraft, and fire at close range. For P-38 pilots, this was a nightmare scenario. The Lightning was never designed to fight this way. It was built for speed, altitude, and firepower, not tight turning contests. But combat doesn't always allow perfect tactics. Pilots reacted instinctively, pulling harder on the controls when threatened. That's when the problem appeared. As pilots increased control input, the P-38's response became heavier and less precise. Instead of tightening smoothly into a turn, the aircraft resisted. Control forces increased, feedback decreased, and pilots often overcorrected without realizing it. In those critical seconds, the Zero gained the advantage. Many pilots believed the P-38 was simply inferior. Others blamed themselves. Commanders debated whether the Lightning was suitable for Pacific combat at all. Some units even preferred older, less advanced aircraft that felt better in a fight. What no one realized yet was that the P-38 wasn't failing because it lacked performance. It was failing because its control system didn't communicate its limits clearly to the pilot. The airplane was stable, strong, and fast, but it was too quiet. And in air combat, silence can be deadly. As the air war over the Pacific intensified, after-action reports began piling up on desks across U.S. bases. On paper, these reports were confusing. Pilots were flying one of the most advanced fighters in the American arsenal, yet the results were inconsistent and often disappointing. Some missions ended in success, but many ended with damaged aircraft or pilots who never returned. What troubled commanders most was that there was no clear mechanical failure to blame. The P-38 engines performed reliably, the airframe held up under stress, weapons functioned as designed. From a technical standpoint, the Lightning appeared sound, yet pilot accounts told a different story, filled with frustration and uncertainty. Again and again, pilots described the same sensation. During high-speed flight, the aircraft felt smooth and powerful, but once combat slowed and turning maneuvers began, the controls became heavy. The airplane resisted sharp inputs, especially during sustained turns. Some pilots reported that the more urgently they tried to maneuver, the less the aircraft seemed to respond. These reports were often dismissed. Engineers reviewing the data saw nothing alarming. According to design calculations, the control forces were within acceptable limits. Test pilots in controlled conditions had not raised serious concerns. From a distance, the problem looked like pilot error or poor tactics. But frontline pilots insisted something was wrong. They weren't saying the aircraft was broken. They were saying it felt unpredictable at the worst possible moments. And in aerial combat, predictability can mean survival. At forward airfields, mechanics were the ones who heard these complaints most often. Pilots didn't vent their frustrations to engineers thousands of miles away. They spoke to the men who worked on their aircraft every day. Most mechanics listened politely and went back to work. One mechanic listened closely. He noticed patterns in the complaints, not just what pilots said, but when they said it. Almost always after close-range turning fights, almost always after pushing the aircraft hard at lower speeds. Instead of dismissing the problem, he started watching the aircraft more carefully during maintenance checks. What he was about to notice was small, subtle, and easy to ignore. But it would change the way the P-38 fought forever. The mechanic, who began to suspect something unusual about the P-38, was not a designer or an officer. He didn't have access to wind tunnel data or engineering blueprints. What he had was experience and time spent around aircraft under combat conditions, something no laboratory could fully replicate. Day after day, he listened as pilots described the same issue using different words. Some said the airplane felt heavy. Others said it felt slow to answer. A few simply said they didn't trust it in a turning fight. These weren't inexperienced flyers. Many were combat veterans who knew the difference between fear and mechanical behavior. Instead of focusing on obvious damage, the mechanic began paying closer attention to how the control surfaces behaved during routine inspections. He watched how the elevator moved when the controls were pulled. He felt the resistance in the system during ground checks. Nothing appeared broken, bent, or worn out, yet something didn't feel right. There was a slight delay, barely noticeable, between control input and response. Not enough to register as a failure, but enough to affect timing during a dogfight. At high speeds, this delay disappeared. At lower speeds and tighter maneuvers, it became more noticeable. The mechanic began to suspect the problem wasn't strength or power. It was feedback. The P-38 was designed to be stable, especially at high speed and altitude. That stability made it an excellent interceptor and escort fighter. But stability can also dull responsiveness, particularly when pilots push an aircraft toward its limits. Most people would have stopped there. After all, the aircraft was performing within design specifications. But the mechanic kept thinking about the pilots who hadn't come back.
During one maintenance session, he began experimenting, carefully, quietly, and without making permanent changes. His goal wasn't to redesign the aircraft, it was to make the controls communicate more clearly with the pilot. What he tried next was simple, reversible, and so unimpressive that others barely noticed. A small tension wire added to the control system. At first glance, it looked pointless. Some even laughed at the idea. They wouldn't be laughing for long.
The addition the mechanic made to the P-38's control system was so small that most people didn't even notice it at first. It wasn't a new component designed in a factory or approved through official channels. It was a simple tension wire, installed carefully so it could be removed without leaving a trace. The purpose of the wire wasn't to strengthen anything or increase performance. It didn't make the aircraft faster or more powerful. Instead, it slightly altered how the elevator controls behaved, changing the way resistance was felt through the control system. To many around him, the idea seemed useless. Some mechanics joked that a piece of wire wouldn't win a war. Others warned him not to fix something that wasn't officially broken. A few officers dismissed it outright, calling it unnecessary and unscientific. The mechanic ignored the comments. He wasn't trying to prove a theory, he was trying to solve a problem pilots kept describing. His belief was simple. If the pilot could feel what the aircraft was doing more clearly, he could avoid pushing it into dangerous situations. The real test came when a modified P-38 was scheduled to return to combat duty. No announcement was made, no pilot was briefed about the change. The aircraft looked exactly the same as any other Lightning on the flight line. Only a handful of maintenance crew knew anything had been altered. When the pilot took off, he felt something different almost immediately. The controls were familiar, but clearer. The aircraft responded more honestly to input. During turns, resistance increased smoothly instead of suddenly. The pilot could sense the limits earlier without forcing the airplane beyond them. Later that day, he encountered Japanese fighters. The engagement played out differently than previous encounters. The Lightning didn't outturn the Zero, but it no longer betrayed its pilot. Maneuvers felt controlled, deliberate, and predictable. When the pilot disengaged and used speed to escape, the aircraft responded exactly as expected. He returned safely. Then another pilot flew a modified aircraft. Then another. And slowly, quietly, something began to change. Pilots started surviving fights they once feared.
It didn't take long for word to spread among pilots, even if no one could explain exactly why certain P-38s felt better than others. Aviators are sensitive to changes in their aircraft. They notice differences in control pressure, response time, and stability almost immediately. Some pilots began requesting specific aircraft by tail number. They couldn't describe the modification in technical terms, but they knew which Lightnings felt right. During combat, these aircraft seemed more cooperative. The controls didn't suddenly stiffen during hard maneuvers. The aircraft gave warning before reaching its limits, allowing pilots to adjust rather than panic. This didn't mean the P-38 had become more maneuverable than the Zero. That was never the case. The Japanese fighter could still outturn the Lightning in a sustained dogfight. But the difference now was awareness. Pilots were no longer surprised by the aircraft's behavior. With clearer feedback, they stopped forcing the airplane into tight turns it couldn't win. Instead, they relied on speed, altitude, and vertical maneuvers, exactly the tactics the P-38 was designed for. When a fight became unfavorable, pilots could disengage more confidently, using the Lightning's superior dive and climb characteristics. Combat reports began to reflect this change. Pilots who had previously struggled now described controlled engagements and cleaner escapes. Losses decreased, successes increased, confidence returned, not because the aircraft had suddenly become perfect, but because it had become predictable. Commanders noticed the shift. They saw improved survival rates and more consistent mission outcomes. The question was no longer whether the P-38 could fight in the Pacific, but why some aircraft performed better than others. Eventually, attention turned back to the maintenance crews. When the small wire modification was discovered, reactions were mixed. Some officers were skeptical, others were intrigued. A few demanded formal testing before allowing the change to continue. But combat statistics spoke louder than opinions. The Lightning hadn't changed on paper, but in the air, it had become a different aircraft. And now, higher authorities wanted to know exactly why.
As reports of improved performance continued to come in, the U.S. Army Air Forces could no longer ignore the pattern. Aircraft that had received the unofficial modification were showing better combat outcomes and fewer losses. This was no longer a coincidence, it was a trend. Engineering teams were sent to investigate. Unlike the mechanic who had added the wire, these teams approached the problem with instruments, measurements, and controlled testing. They wanted to know whether the modification actually changed the aircraft's behavior, or whether pilots were simply imagining the improvement. Ground tests were conducted first. The engineers measured control forces, response timing, and feedback across different speeds. The results were subtle but clear. The tension wire slightly altered the feel of the elevator controls, increasing resistance in a more linear and predictable way. Instead of sudden changes, pilots experienced gradual feedback as the aircraft approached its limits. Flight tests followed. Test pilots reported exactly what frontline pilots had been saying for weeks. The aircraft felt more communicative. Control response at lower speeds was easier to judge. The plane didn't fight the pilot, it informed him. From an engineering perspective, the modification didn't improve raw performance. Turn radius, climb rate, and maximum speed remained the same. But combat performance isn't determined by numbers alone. It's determined by what a pilot can sense and control under stress. Engineers concluded that the P-38's original design prioritized high-speed stability, which made sense on paper. However, in real combat situations, especially at lower speeds, the lack of clear feedback could mislead pilots into pushing the aircraft beyond its optimal envelope. The wire corrected that imbalance. Once this understanding became clear, resistance to the modification faded quickly. What had once been dismissed as a crude field fix was now recognized as a practical solution to a real-world problem. Orders were issued. The modification was approved for wider use. What began as an unofficial experiment on a dusty Pacific airstrip was about to become standard practice. Once the control modification became officially recognized, its impact extended beyond mechanics and engineers. It began to change the way pilots were trained and how they approached combat in the P-38. With clearer control feedback, pilots gained a better understanding of what the aircraft could and could not do. Instead of forcing tight turns, they learned to manage energy, using altitude and speed as weapons, rather than trying to match the Zero's agility. Training units adjusted their tactics accordingly. Pilots were taught to avoid horizontal turning fights whenever possible. Instead, they used high-speed passes, diving attacks, and vertical maneuvers where the P-38 excelled. The Lightning's twin engines gave it excellent acceleration and climb performance when used correctly, allowing pilots to strike and disengage on their own terms. The modified controls made these tactics easier to execute. During steep dives and pullouts, pilots could feel the aircraft's response more clearly. They knew when they were approaching limits and could adjust smoothly, rather than reacting too late. This reduced the risk of losing control and improved overall confidence. As a result, P-38 units became more effective. Pilots reported fewer close calls and better coordination in group engagements. Wingmen could trust each other more, knowing that their aircraft would respond predictably. the Lightning transitioned from a misunderstood aircraft into a specialized weapon. The Zero's strengths hadn't changed, but their impact had. Japanese pilots still relied on tight turns and close engagements, but American pilots increasingly refused to play that game. Instead, they dictated the fight, attacking from above and escaping before the Zero could respond effectively. The balance of power began to shift. What had once been seen as a fatal flaw in the P-38 was now understood as a design characteristic that simply needed better communication between machine and pilot. And that communication had been restored by something almost laughably simple: a piece of wire.
As American pilots adapted their tactics and the P-38's control improvements spread across units, the Zero's dominance in the Pacific skies began to weaken. The aircraft itself had not changed. It was still light, agile, and deadly in close combat. But air warfare was evolving, and the conditions that once favored the Zero were disappearing. The Zero's greatest strength, its maneuverability, came at a high cost. Without armor or self-sealing fuel tanks, even minor hits could be catastrophic. As American pilots grew more disciplined and avoided prolonged turning fights, they began exploiting this vulnerability. High-speed attacks allowed them to strike quickly and withdraw before the Zero could respond. The improved control feedback in the P-38 played a crucial role in this shift. Pilots could now execute precise dives and climbs with confidence, maintaining energy advantage throughout the engagement. They no longer needed to guess how the aircraft would respond under pressure. Japanese pilots noticed the change. Encounters that once favored them now ended differently. American fighters attacked from unexpected angles, refused to turn, and disengaged cleanly. The Zero, optimized for dogfights at lower speeds, struggled to keep up in vertical maneuvers and high-speed chases. Losses mounted. This wasn't because the Zero had suddenly become obsolete, but because the environment had changed. The Lightning was finally being used as intended, and its pilots understood its strengths. By late stages of the Pacific Campaign, the Zero was no longer feared in the same way. It was respected, but understood. The shift wasn't the result of a single dramatic invention or new aircraft model. It was the result of small improvements, better training, and pilots who learned to fight smarter instead of harder. And at the center of that transformation was a tiny modification that helped pilots sense their aircraft more clearly. A change so small that just months earlier it had been dismissed as pointless. Despite the impact of the control modification on combat effectiveness, the person responsible for it remained largely unknown. The mechanic who first added the wire was not celebrated, promoted, or publicly recognized. His name rarely appeared in official reports, and history moved forward without recording his contribution in detail. This was not unusual during wartime. World War II was filled with innovations born out of necessity, many of them created far from design offices and command headquarters. Mechanics, technicians, and ground crews worked long hours under extreme conditions, solving problems as they appeared. Most of their solutions were practical, improvised, and undocumented. What made this case special was its impact. The wire didn't change the aircraft's structure or performance on paper, but it changed how pilots interacted with the machine. It turned confusion into clarity and hesitation into confidence. In combat, those differences mattered more than any statistic. The mechanic understood something that formal testing had missed. Pilots don't fly numbers, they fly sensations, feedback, and instinct. When those elements are compromised, even the best aircraft can become dangerous. Yet recognition was never the point. The goal was survival. As the modification spread and became standardized, it was absorbed into official procedures. Manuals were updated, production changes followed. The origin of the idea faded into the background.
The mechanic returned to his routine duties, maintaining aircraft and listening to pilots. But every Lightning that returned safely from a mission carried proof of his work. This story serves as a reminder that wars are not won only by famous aces or brilliant engineers. They're won by thousands of individuals who notice problems and quietly fix them. Sometimes, the most important contributions are the least visible. When people think about technological breakthroughs in World War II, they usually imagine powerful engines, new weapons, or revolutionary aircraft designs. Rarely do they consider the importance of small, almost invisible changes. Yet, history repeatedly shows that wars are often decided by details most people never notice. The P-38's control wire was one of those details. It didn't add speed, it didn't increase firepower, it didn't make headlines. What it did was improve the connection between human and machine, allowing pilots to make better decisions in the most stressful moments imaginable. Air combat happens in seconds. A pilot doesn't have time to analyze charts or recall technical data. He reacts based on feel, instinct, and trust in his aircraft. If that trust is broken, even slightly, the consequences can be fatal. Before the modification, many P-38 pilots hesitated or overcorrected because the aircraft didn't communicate its limits clearly. The wire changed that relationship. By improving feedback, it helped pilots understand when to push and when to disengage. It reduced surprises. And in combat, reducing surprises saves lives. This lesson extended beyond the P-38. Engineers and commanders began paying closer attention to pilot feedback, recognizing that laboratory performance didn't always match combat reality. Training programs evolved. Design philosophies shifted toward better human-machine interaction. The Lightning story became a quiet case study in how real-world conditions expose flaws that controlled testing can miss. It also highlighted the value of listening to people on the ground, those who see aircraft return damaged, hear pilots describe fear and frustration, and witness firsthand the cost of small design oversights. In the vast machinery of war, it's easy to overlook individual contributions, but without those contributions, progress stalls. The P-38 didn't become legendary because it was perfect. It became legendary because its flaws were understood and addressed.
By the end of World War II, the Lockheed P-38 Lightning had secured its place in aviation history. It was credited with thousands of enemy aircraft destroyed, long-range escort missions, and some of the most important operations of the Pacific War. Famous aces flew it. Historic missions depended on it. But behind those achievements was a quieter story. The Lightning's success was not only the result of powerful engines or advanced design, it was also the result of adaptation, of listening, learning, and making changes where they mattered most. Among those changes, the small control wire stood as one of the simplest and most effective. The wire did not make the P-38 unbeatable. Japanese pilots still posed a serious threat, and air combat remained dangerous until the final days of the war. But the modification helped restore balance. It allowed pilots to fly the aircraft as it was meant to be flown, using speed, altitude, and teamwork instead of desperation. Most importantly, it gave pilots confidence. Confidence in combat is not arrogance, it is trust, in training, in equipment, and in one's own ability to make the right decision under pressure. The wire helped rebuild that trust at a moment when it was desperately needed. The mechanic who first installed it never sought recognition. His contribution was absorbed into the system, becoming just another line in a maintenance procedure. Yet every pilot who returned safely carried evidence of his work.
This story reminds us that history is not shaped only by grand inventions or famous names. Sometimes it is shaped by someone who notices a small problem and refuses to ignore it. A single wire, a simple idea, and a fighter that finally found its voice in the sky.